Okay, so let's start today's session. Mm, So, good afternoon, everyone who have joined. As you know, this is the interactive session where we discuss the doubts and if there are any queries related to the NPTEL course Experimental Physics 2, which is being taken by Professor Amal Kumar Das from IIT Kharagpur. And these interactive sessions, this is the fifth interactive session, and these sessions we have weekly every Saturday 3 to 5 p.m. And I am PMRF Research Scholar Mrinalini from School of Physics, University of Hyderabad. Let's have a recap of last week's discussions. So last week we had done experiments on determining focal length of a concave lens, and we had also discussed and did questions based on focal length of convex lens. Then we had discussed thoroughly applications of mirrors and various mirrors, concave and concave and convex mirrors, concave and convex lenses. So these were these magnifying glass, corrective glasses. This is the use of concave mirror in torches, solar furnace or shaving makeup mirrors. This is in convex, use of convex mirrors in side or rear view mirror of vehicles. So these were the applications we had discussed thoroughly. Then we had discussed and how to find out the working formula for determination of refractive index of liquid using traveling microscope. And okay, so these were the things that we had covered last week. Now this week we are going to focus on about spectrometer and another optical thing that we find in our optics laboratory, which is called prism, which is basically made up of glass. And yeah, further we'll discuss in detail after a few slides. So first let's discuss about spectrometer. So spectrometer is a device that looks like this. This is a schematic of spectrometer here. The basic or the important things in spectrometer are three things. Let me take pen. So the three important things in any spectrometer that we want to focus on is the collimator, which is here. You can see this tube here is collimator. On one of its end we keep the light source. It could be white light, it could be sodium light, or any light that we want to study or perform the experiment with. So this light passes through this collimator, and there is a slit here with which we control how much light we want to pass through this, and then it reflects or refracts from the prism, and then we study after reflection or refraction when this light comes to this tube, which we call telescope or eyepiece. We call it telescope or eyepiece, and there is a cross wire in it that we keep on the image that we see to study various things that we'll again see further. So these are the three aspects. One is collimator, the another is prism table, and the prism kept on it. Third is this telescope or eyepiece. Then after these, so whenever we want to do an experiment, we want to do something called leveling, which is very important, and then we focus on that the beams that we are getting are parallel. That also for this various methods are there. And then in telescope we want to get clear image. For that we do some focusing, like these focus knobs are here, which when we turn them, the distance between screen and this we are basically moving their convex lens. This again we'll discuss. There are lenses inside which we used to focus the get images, and so when we turn these knobs we are trying to focus so that we get clear image. So these are the three things, and then we'll also discuss about prism, many things about this. So these are the three aspects we'll look. And then yeah, whenever we do any experiments we want to find the position. For that there are scales, maybe in another figure we'll see there are scales on this spectrometer which we read, and how to read those scales also we'll see. So yeah, so I was talking that first thing that is very important when we want to carry out any experiment using spectrometer is, so as the name suggests, spectrometer is made up of spectrum and meter, right? The word spectrometer is made up of spectrum and meter. So it's like we get spectrum from after dispersion from prism of any incident light of maybe white light, and then we measure it. So that's why it's called spectrometer. So first thing that we take care before performing any experiment is to level this whole setup. So that we do using something called this spirit level. Okay, this looks like this. It has many in it, otherwise simple small cuboidal thing it is, the basic that we can find, and there is a tube in it which looks like this. So even basic has at least this one. There is some sort of liquid inside it, and a single bubble, air bubble is there. And what we have, how we have to use this is that there are two marks, right? And what we have to be careful is that this air bubble should be between these two marks. When the air bubble is exactly between these two marks, then we can say that the level is, it's flat, it's completely horizontal. So for this, what we'll do, we'll keep this spirit level on this collimator, and there are various adjusting knobs at below bottom of the spectrometer to adjust its height from various sides. So when we'll keep the spirit level on the collimator, and until we get the bubble exactly between these two marks, we'll keep on adjusting the height or the level of the spectrometer. After this is leveled, then we'll keep it on telescope, and after that is also we are getting exactly horizontal. After that we'll do the leveling for this prism table. There are also a lot of screws are there, and using which ultimately when all the three things are leveled, then we are ready to start our experiments. So this is the use of spirit level for leveling the setup. So this is one more picture. Here is what we are calling scale. The scale, which consists of, as I said, we are going to measure. Even in experimental physics 1 course, we had talked about lot of measuring, like measuring equipments, measuring instruments like vernier scale. We are all seeing normal 15 centimeter scales we have seen. Now when we go to any experimental lab, then we need, in our 15 centimeter scale actually we have least count of 1 millimeter usually. Some may have even less least count, but usually we get 1 mm. Now if I want to measure something which requires even better resolution or even smaller least count, then we have what is called vernier scale or screw gauge, where we had understood how we use them and how we take the readings, and how the least count and error is included in these. So these were the things. If you want to read about or understand, you can go to the video recordings of experimental physics first course. But for here, because we are going to use spectrometer, we need to understand here what kind of scale is there in a spectrometer and how we have to take the reading. So this is the scale that we are seeing. I'll show you magnified view, and then we'll try to understand what is there. So this is the magnified view of this scale from different kind of spectrometers. This is called Vernier scale and this is called main scale. This is also, as you can see, is written Vernier scale. Why is it written Vernier 1? I think because there are two Vernier scales here. You will see in an experiment also that we take the reading two sides. So usually we have one scale this side, another scale on the opposite side. So again, this is for another spectrometer. This is Vernier scale, this is main scale. Yeah, now let's focus how we have to take reading using from this scale of spectrometer. So as I told, this smaller scale is called Vernier scale. It has divisions. It doesn't need to be always 30. It depends on the type of spectrometer. So that's why this least count is not constant for every spectrometer. We have two, and we should calculate the least count for particular spectrometer or particular measuring equipment that we are using. And it is easy, and we'll see how it is to be done. So this is Vernier scale. Here we can see it's from 0 to 30, means there are 30 divisions. And this is main scale, usually because the rotation is completing one complete circle, so of course the angle will be 360 degree. Here we are talking about degrees. It's because it's when we are rotating the prism or the collimator, so we are doing it in this circular path. That's why we are talking about degrees here. Unlike when we are talking about some linear measurement, then we talk about centimeters, millimeters, or whatever the instrument is accordingly. So here this 300 means 300 degrees. Okay, it's not written every time, but this is what it means. But this 0 to 30 doesn't mean it's 30 degree, it's just 30 divisions. Okay, so if this is clear, then let's see how we have to do. Okay, so what happens is, whenever we want to take final reading, okay, that we'll see. First I want to find out, so okay, I should have written here, whenever we want to take reading, any reading, so our final reading, this is very important, please pay attention. Final reading consists of main scale reading, this is main scale reading, I am writing in short, plus Vernier scale reading multiplied by the least count of the setup. LC means least count. So whenever we are taking any reading, we have to follow this formula. Okay, now how to find out main scale reading? Or first let's find out the least count. Let's first find out least count of the system. To find out least count of this spectrometer system, the formula is least count of main scale, this is the main scale, minus least count of Vernier scale. Okay, so here first let's see least count of main scale. First let's focus on this. If we'll go step by step, there won't be any mistake. So least count, this we want to find out. For this we are first focusing on least count. How to find out least count of this spectrometer scale? For that the formula is least count of main scale minus least count of Vernier scale. So least count of main scale, here we can see, if I focus at this 280 degree and 290 degree, in between 20 marks are there, you can count. Okay, and these 20 marks, as you can see, starting from 280 and ending at 290, means the difference is 10 degrees. So the difference is 10 degrees and there are 20 marks in between. So what does that mean is that 1 mark is 10 divided by 20, that is 0.5 degree. That means this will be 280.5 degree, 281 degree, as you can see, and 281.5, 282 degrees. So it will go like this and we will reach 290 degrees. So one mark or one division represents 0.5 degree, or we can write it as, you know, we write things in minutes. Like this is degree. If I multiply it 1 degree into 60 minute, this will give me 30 minute. This is also, this is not time. Wait, please don't confuse. This is not time. This is just way of, this also represents, it's a smaller unit of degree actually. So 1 degree is 60 minute, and here we have 0.5 degree, that's why it becomes 30 minute, which we actually, to avoid confusion, because in time we use, we write like this, but here we are talking about angle, so it's represented by this apostrophe or this comma or this sign. Okay, so this means this, we call it 30 minute, but it's representing this angle here. So 1 mark means 0.5 degrees or 30 minute. Now we have to find out least count of vernier scale. So for least count of vernier scale, okay, so let's go to another slide. Why I came here? Because for finding out least count of vernier scale, we want to keep the zero of vernier scale exactly at some particular unit, so that it will be convenient. If I keep it somewhere like this, then it will be a little difficult for me to count that 0 to 30 how many are coming. Okay, so that's why I've just moved it, rotated the main scale, so that 0 of vernier scale is exactly matching to some particular value. So when it's in this position, now I can see here that there are 30 marks on the vernier scale, which again I am reminding is not degree. Okay, vernier scale is not showing degrees, whereas main scale show things in degrees. Okay, so these are just 30 divisions or 30 marks. So 30 marks on these 30 marks on vernier scale, they are covering how many degrees on the main scale? As you can see, 0 to 30, here it's 294.5 degrees it's reaching. That means 294.5 minus 280 will be 14.5 degree. So these 30 marks on vernier scale is covering 14.5 degrees. That means 1 mark on vernier scale represents 14.5 degrees divided by 30. Okay, this will be, let me use calculator to find out what this will be. 14.5 divided by 30, which will be irrational number like 0.48333 and so on. Okay, this will be in degree. If I again write it in terms of minutes, then I'll multiply it with 60 and I'll get 29 minute, right? Because 30, let me show, 14.5 degrees divided by 30 multiplied by 60 minutes, this will be 29 minutes. So that's why, otherwise if I write like this, it's an irrational number, so that's why we were using minute. Otherwise there is nothing wrong in keeping it in degrees also. So this is the least count of, because the smallest value I can measure here is this 1 mark, and that 1 mark is 29 minutes. So this is the least count of vernier scale, and the least count of main scale was 30 minutes. Now as I told, our formula, the final formula will, so the least count of this setup, system, or anything you like to call, you can call, it is least count of main scale minus least count of vernier scale. So least count of main scale was 30 minutes and least count of vernier scale was 29 minutes. So 30 minutes minus 29 minutes is equal to 1 minute. Now 1 minute in degrees is how much? For that we will divide it by 60. Okay, and I will get 1 divided by 60 is 0.016, and again it's irrational number, so it keeps on continuing. If I end at somewhere here, then at least it becomes 0.0167 degrees. So either you can write your readings in minute form, or you can write it, just keep it in degrees, but the procedure is just the same. Okay, first you need to find out least count of system, and the way is this. I hope this is clear. If you have any doubt, you can ask at this point. It will be better to clarify. Okay. Now let's do an example to see how we measure the reading, because I told here, right, whenever we want to measure something, we want mean scale reading, vernier scale reading, and least count. So we understood how to take least count. Now let's see how we read the measurement. So if I have kept collimator at some position, because of which the position of vernier scale and main scale, this is vernier scale, this is main scale. So I have kept the collimator position such that the position of vernier scale and main scale are coming like this, for example. Then main scale reading here is what? The zero of the vernier scale, wherever it is matching the main scale, that becomes our main scale reading. But here you can see that it's not exactly is coincident to any particular marks, it's in between. Then in this case, what should we do? It's similar to what we do with other equipments, that we take the main scale value which this zero has crossed, not the value which is like, even if it's nearer to this another mark, still it has not reached. So we only take that value or that mark as main scale reading which has been crossed by this zero. Like here the zero mark has crossed this, which is actually, if you read, this is 279, this long mark is 279, this is 278, so in between will be 278.5 degrees. Even if it's closer to this 279, still if it has not crossed this line, then we will not consider that. Okay, because that will be taken care of by vernier scale reading, that we will be taking considering later, because main scale reading is not able to give exact value between here, but that will be taken care of by vernier scale. So when we are taking main scale reading, we have to only focus on the lines which zero has already crossed. Like here it has crossed 270, because it's starting from zero from this side and it's increasing in this direction, right? If you will see the whole scale, it is increasing in this direction. So we can see, we understand this is 279, this is 278, and this is 279, this is 278, and in between is 278.5, which zero of vernier scale is crossing. So main scale reading becomes 278.5 degrees or 278 degrees, and the 0.5, if I want to write in minutes just to show you, then it will be 1 degree is 60 minutes, that means 0.5 degree will be 30 minutes, right? 1 degree is 60 minutes, that means half degree is 30 minutes. This is another problem. Okay, so this is another way of writing it in degrees and minutes together. So this is main scale reading. Now vernier scale reading. We have to, what is the vernier scale reading here? Now for vernier scale reading, we have to see which mark on vernier scale is exactly matching with the marks on main scale. So out of these 30, the mark which is exactly matching, here I can see this mark, 10th mark on vernier scale exactly matches with, we'll see what is this value, but this mark, it exactly is matching. We can check, sometimes we also use magnifying glass to, because they are all very close. Some are very far, we can see here, of course it's very far, but some values are coming out to be very close. So to avoid any confusion, we also use sometimes magnifying glass to see which one is exactly matching. Here just for example it is, so either this, it's because of I think this illustration we cannot, it's not actual system, but here if I consider this 10th vernier scale mark to be exactly matching with the main scale mark, then vernier scale okay, let me show you how we write. So here for example here we are taking that the 10th one is exactly matching. Okay, so our formula was our final reading, again let me write, our final reading is main scale reading plus vernier scale reading multiplied by least count. Now what was our main scale reading? So least count we found out, main scale reading is 278.5 degrees, or in minutes if I write it will be 278 degrees and 30 oh, just a minute, okay it's gone, 278 degrees and 30 minutes plus now Vernier scale reading is this 10, which again is not 10 degree, it's just 10 some mark multiplied by least count. We found out the least count of this system was 1 minute, so 1 minute, so it will be 278 degrees 30 minutes plus 10 times 1 minute means 10 minutes. When we'll add this we'll get 278 degrees 30 minutes plus 10 minutes means 40 minutes. Okay, this is in degrees and minutes. If you just want to keep in degrees then it will be 278.5 degrees plus 10 times, and what was the least count? 0.0167 degree. 0.0167 degrees. Okay, after multiplying 278.5 degrees plus this will become 0.167 degrees, and the total will be 278.667 degrees. Okay, if I convert this 40 minutes just to show you that in degrees how much will it be. So this 40, 60, so this, to convert this into degree, 40 minute divided by 60 minute, because 1 degree has 60 minute, this will be 0.667 degrees. So which is what we are getting. So whichever path you follow, it's correct because the procedure has to be correct, then the answer will also be fine. So this was the measurement, the method to follow to read the spectrometer scale. Okay, I hope this is clear. If there is any doubt you can ask me, and otherwise we can continue. So these were the three components of spectrometer that we were talking about: collimator, prism, grating. So yeah, I mentioned these, but I think for detail you can see, you must have already seen this week's lectures by Professor Amal, and there you can, because he has talked about these three things in detail there, so there you can, that's better to learn it from there, and if you have some doubt then you can ask, so that we can here more focus on doing numericals based on this. Okay, so the collimator we use, actually we use some light source from which we use this slit. This is the slit, how it looks like, and we adjust the slit width and height to get reduced number of beams inside, so that we can get it to be parallel. And then there is a convex lens, which when we keep it at focus of this, then it gives parallel light on the other side, which when falls on the prism and reflects back, then in the telescope this parallel ray, when it falls at the convex lens, then it's converged at focus, and when we want to see this image forming here or the light here, Then we want to keep our screen at the focus, because at the focus we'll get the best clarity of this image. And then we have a crosswire here, and this is the eyepiece to make this again parallel so that we can able to see it. So all these things have been very nicely explained in the video. You can watch it there, and here let's discuss further about the prism. So this was also, as were discussed in the videos, there are many types of prism. The one that we want to focus on, the more popular one that we usually use in our optical laboratories, we see around, are these kind of uh, triangular prisms made up of glasses. In these prisms, so when a light is incident on one side of this prism, it disperses, and we are able to see this splitting of white light into its various components, which are these 7 different colors of lights. Colors we see different because their wavelength is different. So that, and since we know, again I mean, when we were talking about refractive index or Snell's law, we were seeing that if this is air and this is glass medium, so we were talking about this thing that the speed of light is more in air, right? Speed of light is more in air and speed of light is less in glass, because this is optically denser medium, and because of this, when there is angle of incidence, this is angle of incidence, then the angle of refraction is R is less than I here, because the speed of light is less, so the ray moves towards the normal. Okay, so here also the same interface is just, here this is air, this is glass, and this is air again. So if I draw normal, this is angle of incidence, this is angle of refraction. Now this angle of refraction we know depends on refractive index of the medium, and then this refractive index is different for different wavelength. That's why the angle of refraction is also different for different wavelength of different lights. Okay, and then there is another interface here. From this again, when it goes out, then it's again there is change in speed, which is different for all these wavelengths. So that's why we see dispersion like this on another side. So here the light is encountering 2 interfaces, air to glass and glass to air, and as a result we get this dispersion or scattering of the incident white light, which is made up of these 7 wavelengths. So okay, moving on. Yes. So let's understand what are the different parts of a prism. So in a prism like this, where 2 faces which are opposite to each other are triangular like this, and the sides are 3 rectangle. Okay, so this is kept opaque, these triangles are put opaque, and the rectangle, you can see, if I'm seeing from one side this prism, then there is one side, 2 side, third side. All these 3 sides, these 2 triangles will be connected by these 3 rectangles. So one at the down also is kept opaque. So only this is opaque, the one triangular side at the back is opaque, the one rectangular side at the bottom is opaque. Now only this side and this side are transparent. So when the light is incident, only it's reflecting or refracting from this side, and reflecting or refracting and coming out from this side. Okay, so out of there are 2 triangular sides and 3 rectangular sides, so total 5 faces are there for this prism, and in these 5 faces, 3 faces are opaque. We don't want any reflection or refraction from other sides, otherwise everything will get mixed up and we won't be seeing what we want. And the two faces, which are rectangular, are kept transparent. So this is how we make this prism. And then let's understand different parts of it. So dispersion of prism is like, dispersion is the process of white light splitting into its component colors when passed through a prism. Why? Because different colors of light have different wavelengths, and the prism material, whatever the material has been used to make this prism, so that material's refractive index varies for different wavelengths. So refractive index is function of wavelength actually. For different wavelength, it's different, because we know in glass or any other denser medium the velocity changes, right? Velocity changes, say if it's decreasing, that means one of these also has to decrease, that is wavelength decreases, because frequency doesn't depend on the medium, frequency depends on source. So frequency remains unchanged, velocity decreases, and also wavelength decreases. So refractive index is function of wavelength. So as I explained, when white light hits here, it splits, and when it again hits on the second interface, it splits further. Why? Because refractive index of this material is different for different wavelength light. That's why their angle of refraction is different. So this is how we see dispersion because of a prism, and not any normal. If you will take a cuboid of glass, you will not see dispersion there. Light which will go here, it will get refracted, and when it will be incident on another surface, it will come out all joined together. So you will not see dispersion there. That's why we use this particular shape of prism to see dispersion. Okay. Now further, there are different things that we need to understand. When we have a prism, which is made up of three straight lines, then if this side and this side are kept transparent, means from here I am going to incident a light, and from here I am going to get an emergent light, or vice versa, then the angle made between these two sides is called angle of prism. We usually represent it by capital A, and it's called angle of prism. Maybe further we have discussed it again. Oh, that is experiment. Okay. So this is called angle of prism. Okay. Now there is one, let me take more slides here. Just a minute. It's a little slow. Okay. First, let me explain you something here. So, when we have a prism, I'm trying to make a bigger one. Sorry about the shape, but okay, let me try once again to make a better shape. Just consider it's a nice triangle, okay? So, and this is the transparent side, this is the transparent side, and the angle made between this is what we called angle of prism. Okay. Now what happens is, as I said, there are two interfaces here. This is made up of, let's say, glass. Okay. Outside is air all around this prism. Now if I draw a normal to this, surface, this is first surface. Let's call it ABC. Then AB is the first surface, let's say, and AC is the second surface. Second surface or second interface. It's better to call interface because here two different surfaces are meeting. So that's why it's better to call interface. So this is first interface, this is second interface. For this also, if I draw normal, it is like this. Why I am drawing normal? If you recall, angle of reflection laws or refraction laws, in both laws we talk about angle of incidence with respect to this normal, right? If there is a light incident at this point, then we measure the angle of incidence from this normal to the surface. That's why I am drawing this normal. Okay, it's never taken from the angle of incidence. At least if I am saying the angle between the beam and surface is something, then it's different case. But when anybody is talking about angle of incidence, then that means the angle between the beam and the normal to the surface. So that's why I have drawn this, and this is the angle of incidence. So air, refractive index is 1, glass, refractive index of glass is more than refractive index of air. Okay, this is optically denser. So what will happen? The speed of whatever beam it is, its speed will decrease, and the beam after refraction at this interface, it will move towards normal. So it will be less than I. So it will move. Okay, this is just for example, because actual value of refractive angle will depend on the value of what kind of beam it is and what is the refractive index of this. So this R will be less than I. Now when it will reach, then if I take the normal here, then this will be another refractive angle. You can call it R1, R2, or this will be like incidence angle on this side. But usually for prism, what we call this side refractive angle 1, and this we call refractive angle 2. And then because outside when this light will come here, it's rarer medium, so it will move away from it. It will move away. That means, and this is called emergence angle, and E will be more than R2. Okay, so when this happens, if what we need to understand, so angle of incidence here comes inside, gives refractive angle 1. When it's incident on second interface, we get second refractive angle, and what comes out with respect to the normal, the angle it makes, we call it emergence angle. So this E is called emergence angle. Okay, angle incidence angle is represented by I. R, refractive angle, angle of refraction, and E is emergence angle. That light went inside the prism and it came out with this particular angle. So when this happens, what we can see is, if this prism is not here, then the light will go something like this, right, in a straight line. But because of presence of this glass or whatever materials prism, the light is finally going in this direction. So if the prism would not be here, it will go in this direction, which was like original path, but because of prism, it's coming to this direction. So this deviation in the direction of light, this angle, okay, is what is known as angle of deviation. Okay, it can be represented by delta or delta m or whatever you want. But just to repeat, if the prism is not there, then this light will go in straight path in this direction, but because of the presence of this prism, it's undergoing refraction at this interface and then undergoing refraction at this interface. So finally it's emerging in this direction, and the change in direction because of the presence of this is called deviation, because it's deviating from the original path because of presence of this prism. This angle is called angle of deviation. Okay, so this, because we'll do many numericals based on this, and also we'll see how to find out how to derive the formula for these things. So but this is just to first make it clear that what do we mean by angle of prism and what do we mean by angle of deviation. Now next what we have, so this is just for example that there are these two, red has maximum wavelength out of these 7, violet has minimum wavelength, right? Red has maximum wavelength, we use it, that's why in various places, so that we will able to see that thing from far away. So these are together means we will see white, and when they enter, because they have different wavelength, the refractive index of this prism for both these lights will be different. The refractive index value will be more for this, and that's why its deviation is more, and it will come out to be here, whereas red will be here. So in between, all will be dispersed in between if they are there. So this is how it happens, because the basically refractive index depends on wavelength, so that's why they split and come out like this. Now before we do the understand the angle of prism experiment, that how to perform the experiment to find out angle of prism, first let's understand various as I said, theories and working formula. So the refractive index, as I said, depends on wavelength. So the relation between refractive index and wavelength is given by something called Cauchy or Cauchy relation. Okay, this relation says that refractive index, which is function of wavelength, is given by A plus B over lambda square. Okay, where A and B are constants, actually called Cauchy's constant. Okay, and they depend on the material medium, what kind of material we have used for this prism, they depend on that. So for this, like refractive index for this glass prism, the A and B parameters will be different, and if this prism is made up of something different, then it will be different. So basically this is the relation between refractive index and wavelength given by Cauchy's relation. So this is general idea. Now to find out, so what we had, let me read. So this is what we are showing here, that this is normal to the first interface. This is angle of incidence, which is this angle of refraction. This is 1. Okay, so here, okay, this is some new concept, let me tell you. So here, as I said, this is one refractive angle, this is another refractive angle, and this is angle of emergence. Now something we need to understand, this I told is deviation angle. Okay, now there is something known as angle of minimum deviation of a prism. So we already discussed and understood what do we mean by angle of deviation. Okay, that from original path how much the emergent ray has deviated. But what do we mean here by angle of minimum deviation of a prism? So what happens in a prism, the angle of deviation decreases with increase in the angle of incidence. This angle of incidence, if I keep increasing, if I move it here, it will be the angle of incidence will increase. If I move it here, it will be even larger. So when I increase the angle of incidence, the angle of refraction, the angle of deviation decreases, okay, up to a particular angle. This angle of incidence, where the angle of, so what, in the particular situation, when the angle of incidence, where the angle of deviation in a prism is minimum, is called minimum deviation position. For that particular value of angle of incidence, where the angle of deviation, okay, the original had to go here, just this extension, then this angle D is angle of deviation. So in that position, when angle of deviation is minimum, we call that as angle of minimum deviation, and this happens when this refracted ray is parallel to the base. This situation of minimum deviation to the incident light happens when at that particular incidence angle which makes the refracted angle to go parallel to the base. Okay, in that situation the deviation is minimum. Okay, in minimum deviation the refracted ray in the prism is parallel to the base. In other words, the light ray is symmetrical about the axis of symmetry of the prism. The light ray is symmetrical on both sides. Also the angle of refractions are equal. So in this situation we were seeing we had two different angles, R1, R2, but as I said, when this angle of deviation is minimum, the refracted ray is parallel to the base, and because of this R1, R2 are equal. Okay, in this situation R1, R2 are equal, and also the angle of incidence and angle of emergence are equal. Angle of incidence and angle of emergence are equal, and this refracted ray is parallel to the base. So these things happen when the angle of deviation is minimum. Okay, that's why it has this particular situation has special name. So this was another aspect. Now let's calculate what is the formula of angle of prism when we have this kind of situation. Okay, I need one slide. So again, I think if you consider this itself, this image, to derive the formula. Okay. Maybe I need new slides also. Let me see. Let me paste it everywhere in case of any. Okay. Fine. So we understood angle of deviation and also angle of minimum deviation. Now let's do some derivation. So this is again the same thing. Now let's see what happens. What is the relation between angle of refraction and angle of prism, which is this A. These dots are, I told you, right, these are angles, so don't just confuse. Okay, in this, for this diagram, if you consider the triangle OPQ, which means, where is my cursor? This OPQ. If you consider this particular triangle, then in triangle OPQ, we know all three angles, internal angles of a triangle, the total is 180 degree. So using that rule, we know this angle A, which is this, okay, and then this angle OPQ, plus the angle OQP, the sum of all these three will be 180 degree. It's the property of a triangle. Now, and this angle A is angle of prism, which we want to find out what will be its value for any general prism like this. So angle A will be 180 degree minus angle OPQ minus angle OQP. Okay. Now you see here angle OPQ. Okay, focus on angle OPQ here. This is angle I am talking about. What is it? You know this gray line is normal to this interface. That means this angle is 90 degree and this angle is also 90 degree, right? That means that 90 degree, I want to find out what is the value of OPQ. Now this 90 degree, because this gray line is making is normal to this OP surface, so it's making 90 degree here, right? And this other side, and this 90 degree consists of angle R and the angle OPQ that we are interested in. So from here I can say that angle OPQ plus the angle R is equal to 90 degree. From this, angle OPQ is equal to 90 degree minus R. Similarly, for angle OQP, the same thing, right? This gray line is again normal to this interface, so that means this angle is 90 degree, and from this 90 degree angle is made up of angle R, which is a refraction angle, and the remaining part that we want. So for angle OQP also it is made, it will be 90 degree minus R. We are particularly here talking about this, okay, let me take it as R1, R2. Just assume it's not the minimum angle deviation case, and here the R1, R2 are different, and this is also some emergence angle. Let's consider for generic case. In that case it will be R1 and this will be R2. So these values, when I'll substitute here, I'll get 180 degree minus OPQ is 90 degree minus R1, 90 degree minus R1, OQP is 90 degree minus R2. Okay. When I'll remove the brackets or open the brackets, I'll get minus 90 plus R1 minus 90 degree plus R2. Okay. So 180 degree minus 90 degree will be 90 degree, and again if I subtract 90 degree from it, that means basically they are cancelling out and I'll be left with R1 plus R2. So what I'm seeing here, angle of prism is sum of angle R1 and angle R2. Okay, and in the case of minimum deviation situation, R1 will be equal to R2. That means angle of prism will be 2 times the refractive angle, or R will be half of angle of prism. This for the minimum angle deviation situation. So this is one relation. Now we'll try to find out some other relation as well using the same, for the same prism. We want to find out angle of incidence. Okay, let's see how we'll get that. So again, first let's take generic case, that is, this is R1 and this is R2 and this is some emergent angle which is not equal to incidence angle. Now in triangle RPQ, focus on triangle RPQ. Okay, focus on this, and here again we know sum of all internal angles of a triangle is 180 degree. Let's start from there itself. That means angle RPQ plus angle RQE plus angle PRQ is equal to 180 degree. All these three angles I have covered. Okay, all these three angles I have covered. Now since angle PRQ is actually this whole thing is 180 degree, right? This D is angle of deviation and this whole angle is 180 degree because it's straight line. We know, right? Straight line is 180 degree angle. One part of it is D. So remaining part will be 180 degree minus d. So this angle PRQ is 180 degree minus the angle D. Using this relation, our this equation changes to angle RPQ plus, oh sorry, this is angle RQP plus 180 degree minus angle D, because this angle D is a known variable, is equal to 180 degree. This will be cancelled and we'll get, I'll take this on right side, then it will be angle D is equal to angle RPQ plus angle RQP. Now this RPQ is what? So angle RPQ is RPQ. As you can see, what I want to tell you here is, if you focus this normal and this incidence angle, let me show here, like this is the surface, okay, this is the incident light and this is the normal. So this is what we call angle of incidence, and this normal and this angle of incidence, they are crossing each other in this situation. Here we know something called vertically opposite angle, that these two things, these will be equal. This line crossing this another line, okay, I am talking about this incident light and this normal, they are crossing each other. So the angle between this is the incident light and this is the normal, so they are the same things and the angle between them will be same. So this will also be I. But what is this? This is actually, this whole thing will be I, which will go and give us deviation, right? But this angle of incidence is made up of two parts. One part of it is R1, because it's not following that path. In fact, it's coming closer to the normal and giving us R1. So this I is made up of R1 and this RPQ, which we are interested in. So I'm just trying to find out the values of these unknown angles in terms of the things that we know about the situations here. So this means angle RPQ is angle I minus angle R1. Similarly, for angle RQP, again the same case applies, and we'll be able to find angle RQP is equal to, it will be angle of emergence minus R2. Okay. So putting these values here, angle of deviation, which I am representing by delta, or you can represent by, I'm representing by angle D, you can also represent it using delta. So this angle of deviation will be RPQ means I minus R1, and RQP means E minus R2. So this will be the value if I1, I2 is not same. If it's same, okay, one more thing, this I plus E and minus, if I take out common, then it will be R1 plus R2, right? And you know R1 plus R2 is angle of prism. So this angle of deviation, I can write angle of incidence, angle of emergence minus angle of prism. So this is one more relation that we got to know, that we will do many numericals on this. Now if the case of minimum angle of deviation comes, that means the refracted beam of light is parallel to the base. That means angle of incidence is equal to angle of emergence. That means R1 is equal to R2. When these three conditions happen in minimum angle deviation case, that means I plus E, that means 2 times I, and this is angle of emergence, of course. So If I want to find out the value of angle of incidence from this situation, it will be delta plus angle of prism divided by 2. This is another value that we get to know. Okay. Now there is one more formula we need to consider, which is about refractive index of this prism in relation to angle of deviation, angle of prism that we know. This we can also write as simply as A. That is also correct. So refractive index N21, that is second medium with respect to one for air medium, will be from Snell's law, of course. Okay, from Snell's law, how we can write is refractive index of air or first medium sine of incidence angle is equal to refractive index of second medium sine of r. So when we write it as, I'll write it as sine I divided by sine r, that means mu2 divided by mu1, right? This comes from Snell's law that we had discussed when we discussed refraction laws. So taking ratio of sine I by sine r, then other side it will be the ratio of refractive index of second medium to refractive index of first medium. This we represent in short by this n21, means it is the ratio of refractive index of second medium with respect to refractive index of first medium. So this n21, when we want to find out, calculate for a prism like this, it will be sine. Now I is this delta plus A by 2. Delta plus A by 2. But this is when we are talking about minimum angle of deviation. Okay, keep in mind. So this thing, when I am talking about minimum angle deviation, divided by sine of A by 2. Again, how I got A by 2? When we are talking about minimum angle deviation, then R1 is equal to R2 and R is half of angle of prism. Using this information, this is another formula that we got. So these are various things that we can find out about why we derive these formulas, so that we can, if we know other parameters, one or two parameters, we can find out the other aspects about this kind of situation on the prism. So we'll do many numericals to understand this thing. So these were the things that I think theory wise it's fine. We discussed about spectrometer, how to find out least count, how to take a reading, then different parts of a prism, and then how to find out. We derive these formulas, and now we understood also and we derived also. Now using these formulas directly, let's do some numericals. Okay, so before that, there was an experiment in this week. There was only one experiment which was on angle of prism. Actually, there was another experiment also on Schrodinger's way of making parallel beam. That again you should see the lecture, because here it will be unnecessary repetition, and because here we more want to focus on the numerical. We won't have sufficient time for numericals. So this is the angle of prism experiment. In detail you should watch the video. What basically we are trying to do is, one side we have our collimator, which is acting like source of the incident light. Parallel lights come, they refract from both these transparent side of prism, and then we'll put our telescope to one side and then take measurement, then keep it on opposite side, then take measurement, and we'll repeat it several times. And from this relation that I have just found out, we know angle of prism is okay. So what we'll do, when we'll take opposite side, the difference here will be 2 times A, and we'll subtract these values. So we'll get this 2A, and when we'll take half of it, we'll get A, which will be the angle of prism. So this is the basic thing that we want to do. And for detail how we have to particularly move and focus, these things are need to be taken care, which you can understand from the video better, because there actual demonstration is there. Okay, so now let's start with the questions, numericals. So these numericals, there are 10 problems that I've brought. These problems are from last year's same course. So last year when this course was taken, these were the questions that were given as assignments. So because I cannot solve for you this year's assignment, of course, but these questions are from last year's assignment, and they will be, of course, very much helpful because it is for this week itself. So if you understand these here, you will be able to solve your assignments also. So let's start with first question. So the question is refractive index of the material of prism. So this question is about prism itself. Okay, and we are given that refractive index of the material of prism is 1.5. What is the angle of minimum deviation? So we need to find out this. It's asking angle of minimum deviation. So this is what we need to find out. And refractive angle of prism is 60 degree. So here they are talking about minimum deviation. That itself says that the situation is like this, right? What? Angle of incidence is equal to angle of emergence. Both refraction angles or angle of refraction are same. That means refractive angle of prism, there should not be confusion that which refractive angle they are talking about, because it's situation of angle of minimum deviation, so both the refractive angles are same. Let's represent it by R. Okay, now we need to find out delta M. So just now we derived one formula which says refractive index is given by sine of, this is actually refractive index of second medium by, I told you, refractive index of first medium. Now refractive index of first medium, which is this air, refractive index of air is 1. So that's why I can simply write it as mu2 also. So this formula is sine delta M plus A is angle of prism, divided by 2 divided by sine of A by 2. So the formula for generic case, you know, the formula was would be different, but for angle of minimum deviation we can write it like this. Otherwise there will be separate I, E and other things, but for minimum deviation case we have this direct formula. So this mu2, mu1 is 1, so we are left with mu2, and value of mu2 or this glass medium or prism medium is given to be 1.5. So 1.5, right? And mu1, which is air, refractive index is 1. So 1.5 is sine of, now delta M we need to find out. Angle of prism also has been given. Oh, sorry. So this is not refractive angle of prism. This is, actually they are calling it refractive angle of prism, but this, what they mean is angle of prism. This is a mistake. So they are calling it refractive angle of prism, but this is A. Okay, this is what they are talking about. So A is known and it is 60 degree. Okay, so this is 60 degree divided by 2 is equal, divided by sine, 60 by 2 means sine 30 degree. Now this sine 30 degree, let's multiply this to this side. It implies, now sine 30 degree is 1 by root 2, I think. Sine 30 degree is, let me check. Sine 30 degree is 0.75, and I will multiply it this side. Okay, and this side we'll have sine of delta M plus 60 whole divided by 2. Now when we'll multiply 1.5 with 0.75, multiplied by 0.75, okay. minute. No, wait. Sine of 30 is 0.5. Sine 30 degree is 0.5. Okay. And 1.5 multiplied by 0.5 is 0.75. Okay, 0.75 is equal to this. Now I want to remove this, so I'll take sine inverse on both sides. Sine inverse of this, then sine inverse of this means I'll get delta m plus 60 divided by 2. Sine inverse of 0.75. Okay, let's find out. Sine inverse of 0.75 is, the value is 48.5904. So you also need to use your calculator for this. Sine inverse of this gives this, which is equal to delta m plus 60 divided by 2. Now I want to find out delta m. That means delta m will be 2 times 48.5904. This whole thing I'll subtract 60 from this. Then I'll get angle of minimum deviation. So let's do this. Multiplied by 2 is 97 minus 60. So I am getting 37.18, and then they are further here. Our answer is up to 2 decimal digits, so I am keeping up to 2 decimal digits only. 37.18 degree is the correct answer here. Okay. Now the next question. The refractive index of a prism, of a given prism material, is √2. Okay, so refractive index of material is √2, and the angle of minimum deviation. Okay, so angle of minimum deviation is given to us. Again, angle of minimum, I think it's always better to draw the diagram so that you have all the information in front of you. Like when they are talking about angle of minimum deviation, this of course is a straight line. Angle of minimum deviation, so you draw a diagram like this to be clear that it's parallel. If you want, you can make this also. This is R, this is R, so that information is clear in your mind. This is I, and this is also I, because it's case of angle of minimum deviation. Okay, we have to find out refractive angle of the prism. Refractive angle of the prism means this A, which we simply call angle of prism also. So this is same thing as the same formula we will be using, only the known and unknown parameters are different. So the equation will use refractive index, again mu2 by mu1, or this, but mu1 is 1 because outside is air, so I can simply write it as this, which will be sine of delta m plus a by 2 divided by sine a by 2. Okay, mu2 is √2, sine of delta m plus a by 2 divided by sine a. I need to find out, okay, we need to find out angle of prism. So this side is unknown. It will be 1 over √2 sine of this thing. Now delta m is given to be 30 degrees, and a we need to find out. Okay, so what we can do further is, here sine a by 2, if I take 2 mu, I hope this is correct. Yeah, this is the formula. I want to find out sine a by 2. If I take it to other side, it will become √2. No, this is same. what I want to do with this is this. Sine of delta m plus a by 2. This is inside, right? The actual formula. Where is the actual formula? Yeah, this 2 is inside it. So here, what we can see is I can write how I can write this. Okay, I'm sending this root to this side, and here I'll be left with sine 30 degree plus a by 2 and sine a by 2. So what I can do here is this root 2 I can write as 1 by root 2 divided by half. How? Because when I'll solve this, it will be 1 by root 2 divided by 1 by 2, which means 1 by root 2 multiplied by 2. So it will be root 2. So I am just rewriting it in this form. That was a rough thing that we did. That means root 2 I can write it as this. It is correct. Why I am writing like this? Because so that I can find out the values easily. Now 1 by root 2 is what? 1 by root 2 is actually sine 45 degree. I'll write it here. 1 by root 2 is sine 45 degree. And half is sine 30 degree. That means this thing is equal to sine 30 degree. That means a by 2 is equal to 30. That means a is 60 degree. Okay. So this was easy to find out. Otherwise, what else you can do? We have to take sine inverse on both sides, and then we'll find out. If you can do some trick like this, then it will be even more convenient. So the correct answer, which is angle of prism, is 60 degree. Third question. A ray of light is incident at 45 degree on a prism of refracting angle of 60 degree. Be careful, this refractive angle they are calling angle of prism, because from that particular angle only the refraction is happening. I told other sides are opaque, so refraction cannot happen from there. So only this angle of prism, which we are calling, this is the only angle from which refraction is happening. So that's why it can also be called refractive angle of the prism. So a ray of light is incident. This is the normal to the surface. A ray of light is incident at 45 degree on a prism of refractive angle 60 degree. What is the angle of emergence from the prism? There will be some deviation, and then again this will be R1, this will be R2, and then there will be angle of emergence. Refractive index of material is given, which is root 2. Now we need to find out the angle of emergence. We know angle of prism, we know angle of incidence. So what we can do here is, we have two interface. Interface 1, which is this A, I can call it P. Let's call this B, let's call this C. This is PQ. Just this point I'm calling P and Q. Okay. So this interface APB, this is first interface, and this interface AQC, this is second interface. So let's apply Snell's law for this first interface. Okay. Now using Snell's law for interface APB, for APB interface or surface. For APB interface, when I apply Snell's law, outside the medium is air, inside the medium some optically denser medium, we can call it glass or something. I mean, there is medium different outside and inside. So Snell's law will be the refractive index outside of air sine I is equal to this refractive index of inside. Let's just keep it mu, because Why should we call it glass? They have not mentioned. So just refractive index of second medium, which I am just representing by mu. Let me write here. Refractive index of this prism is mu. Okay. And then sine of R1. Now this I is 45 degree and mu A, air refractive index is 1. So this will become sine 45 degree is equal to, now mu is root 2 sine R1. This is one equation. Now applying Snell's law for another interface, which is AQC interface. Okay, for this interface, when I apply Snell's law, my equation will be refractive index inside the prism, which is a mu sine R2 is equal to refractive index outside, which is air sine E. Refractive index of this medium is root 2. Angle I don't know. Refractive index of air is 1. And emergence angle again I don't know. Okay. But what we could do from this one, oh, I should have solved this one. Let's solve further. Sine R1 will be sine 45 degree divided by root 2. Sine 45 degree is 1 over root 2 actually. Sine 45 degree is 1 over root 2, and when we will divide it by root 2, it will be 1 by root 2 divided by root 2 means divided by root 2 means 1 over sine 45 log means okay. Divided by root 2 means multiplied by 1 over root 2. It will give us half. Okay. So sine R1 is half. That means R1 will be, what value of sine gives us half? Like it's taking sine inverse of half. Sine inverse of half. So 30 sine 30 degree actually gives us this. Sine inverse of half is 30 degree. Okay. So that means this R1 is 30 degree. This one thing I found from equation 1. And now how to find out R2? So if you remember, I can take back also, we had found this see this, for a prism we had found out that angle refractive angle 1, refractive angle 2, when we add them we get angle of prism. So using this relation, R2 will be what? So what we had derived was R1 plus R2 is equal to angle of prism. R1 I know, angle of prism I know, so R2 will be angle of prism minus R1. Angle of prism is 60 degree, R1 is 30 degree, right? That means R2 is 30 degree. So when I put it here, sine 30 degree is half. That means root 2 by half is sine of E. Now this will be 1 over root 2, and when we get 1 over root 2, when the angle is 45 degree, that means emergence angle is 45 degree. Also you can see here R1 and R2 are same. That means it's minimum angle deviation case. That means our angle of incidence, which is given to be 45 degree, should be equal to angle of emergence. So you don't even need to do this. If here you got refractive angle 1 is equal to refractive angle 2, when we use this relation R1 plus R2 is equal to A. From this you can see both refractive angles are same. That means it's angle of minimum deviation case. That means angle of incidence is equal to angle of emergence. So directly also you could have used this. Angle of emergence is 45 degree. Just the correct answer here, B option. Now question number 4. The refractive angle of a prism is 60 degree. Again, let's draw. It's always good to draw, right? I said. Okay. Angle of prism is given, which is 60 degree. Refractive index of prism material, refractive index of air 1, refractive index of this material is given √2. What is the minimum angle of deviation of a ray passing through the prism? They are asking us to find out this minimum angle of deviation. Now we will use our formula. Refractive index of medium, refractive index of, let's just call it air, is equal to sine of delta m plus a by 2 divided by sine of a by 2. This mu a is 1, only we are left with mu, which is √2. Now what all the values we know? √2. Okay. Substituting the values, delta m I need to find out. A is 60. This a is 60 means this is 30. Now sine 30 degree is half. When this half will go there in multiplication, it will be 2√2. No, wait. This, okay, it's in division here. Wait. This is half in division. So it will go, then it will remain in multiplication half. Then it will be sine delta m plus 60 degree by 2. Okay. This will be 1 over √2. And when we get 1 over √2, already we have done so many times the same things. We get 1 over √2 when the sine of 45 degree is there. That means delta m plus 60 degree, you can actually take sine inverse on this side and then calculate, but we know already 1 over √2 is sine 45 degree. So this means the angle is 45 degree. So this will be delta m will be 45 degree multiplied by 2, okay, minus 60 degree. So this will be 90 degree minus 60 degree, that means 30 degree. So the angle of minimum deviation for this particular prism will be, when the angle of minimum deviation will be 30 degree. This is the correct answer. Now the next question is the refractive angle of a prism. Again, let me first draw the schematic of prism. Refractive angle of prism is 75 degree. This is 75 degree now. Okay. And the refractive index of its material is √2. Same. Outside, let's consider air. We are considering air only all the time. At what minimum angle a ray can be incident? We have to find out I minimum. Okay. It's saying what minimum angle a ray can be incident so that it will be able to pass through the prism. What this question wants us to do is actually, let's understand what it's asking for. So we know there will be, if there is a ray incident on prism, then it will undergo refraction and then it will come out. This will be angle of emergence. And we were also talking, if I increase the angle of, just in this case, or let's try to understand this from what we had understood last week, something known as critical angle. Like if there is air medium and there is, say, like glass medium or water medium, some optically denser medium, this is normal to the surface. If the light is incident, I'm sorry, okay, so if the light is incident here, this is optically denser medium, means the light speed will decrease and it will move towards the normal. So that means this R will be less than incidence angle. If I further I mean increase or decrease. So okay, this is on this side. Now what happens when the ray of light will come out of this glass medium? So this will be incident here somewhere, okay, and this is optically rarer medium, so incident light will move away, right? And this, so what happens is we had seen that there is particular value. If we keep on increasing the value, if I keep increasing this, then it will go even further. If I again increase this angle of incidence, it will again go farther away from the normal, the outside going one. Okay, the larger the angle of incidence is in the medium, outside it will be farther away from the normal, and there will be one particular angle at which it will just be parallel to the surface, means it will just be outside. And if I, this is called critical angle, and if I take incidence angle more than this critical angle, then it will come inside, it will not go outside, it will come inside, and this is called total internal reflection. So what it's asking is the same thing. If I keep on increasing this angle of incidence here, maybe a situation will reach when it will, instead of going out, it will just come back. So we have to find out at what minimum angle, okay, it will be able to just pass through the prism. Means just pass means the angle of emergence will be 90 degree. This will be the angle of emergence, because if I increase further, then it will come out. So this is the angle of emergence when I'm in the situation when it's saying it has to be 90 degree, means it has to just come out of the prism. So this is known here, and we have to find out I minimum. So I hope the situation at least is clear what this question exactly wants us to do, and I just tried to tell you using the this rectangular slab situation. Okay, the same thing is applicable here. So maybe I'll need one more slide. Okay, so for this particular case, let's use Snell's law at interface 1 and 2. So for this interface, okay, first interface, the equation will be mu a sine I is equal to mu sine r1, like this will be r1, right, and this will be r2. So in this, or actually I think it's better that we, because here at least we know this angle, so let's first apply this Snell's law at the second interface. Let's give some name here, it's always better, AQC and APB. So let's apply Snell's law for, let's apply Snell's law first for this interface AQC. Okay, here what will be the equation? Mu sine r2 is equal to mu a sine e. Refractive index of air is 1, sine e is 90 degree. Now sine 90 degree is 1, and refractive index of this is given, which is root 2. Root 2 sine r2 is equal to 1, which implies that sine of r2 is equal to 1 over root 2. That means r2 will be 45 degree, right, because sine of 45 degree is 1 by root 2. So applying Snell's law on this second interface here was useful because we could find out second refractive angle from this. Now applying now let's apply the Snell's law for interface, another interface which is APB. Here the equation will be mu A sine I is equal to mu sine R1. Now one thing, here I also I need to find out and R1 also I need to find out. So one thing at least we need to know. Here if you recall, R1 plus R2 is equal to our angle of prism. This equation we can use because we know angle of prism is 75 degree. From this I can find out R1 is 75 degree minus 45 degree, that is 30 degree. Using this equation will become refractive index of air is 1 multiplied by sin I is equal to refractive index of this prism is given to be root 2 and sine of R1 is 30 degree. Sine of 30 degree which is half, that means root 2 multiplied by half, that means this is 1 over root 2. Now sine I is equal to 1 over root 2, that means I is equal to 45 degree, right? That means the incidence angle should be 45 degree at least to get it, so that we get some emergence light. So this is this equation. Now okay, I didn't have to use the extra slide, but so the sixth question is the refractive angle of prism is A. Again let's quickly make this. No, refractive angle A, let's call this prism ABC. A is refractive angle of a prism is A. Okay, they are just calling it A, and the angle of minimum deviation is this. Angle of minimum deviation is 180 degree minus 2A. Find out the refractive index of the material of the prism. Now we know the relation. Refractive index of material of prism, which we represent by mu, is given by sine delta m plus A by 2 to the ratio sine of A by 2. Using this, now substituting delta m's value, I'll get sine of 180 degree minus 2A plus A divided by 2 divided by sine of A by 2. Now A minus 2A is minus A, that means sine of 180 degree minus A divided by 2 divided by sine of A by 2. Okay, now what we have to do is, if I divide these two things by 2, I'll get sine of 90 degree, right, minus A by 2 and sine of A by 2. Now sine of 90 degree minus theta is cos theta, cos A by 2, because cos theta plus, sine, this is not that actually, but sine of 90 degree minus theta is cos theta. This is the relation you should remember. Sine of pi by 2 or 90 degree minus theta is cos theta. Okay. So using that we'll get cos A by 2 and in denominator we'll have sine A by 2. Now cos over sine is what? This side is refractive index of material, we are not given, we don't have to find out also. So this cos over sine is cotangent A by 2. So refractive index for this particular case will be cotangent of A by 2. That means this is the correct answer, option A. Seventh question is, refractive angle of a prism is 60 degree and the refractive index for the material, now maybe different kind of material or glass is used which has refractive index of 1.5. When a ray of light is passed through the prism and its angle of emergence is 90 degree, then find out the angle of deviation. This is same case. If Angle of emergence is 90 degree. Angle of emergence is 90 degree. Means it's what we are talking about is that minimum angle, incidence angle through which it should go so that it just comes out, that we had used earlier, right? Now again, we know angle of emergence, so let's apply. Here I'll have R1, here I'll have R2. So let's apply first A, P, B, C, Q. Just this point I'm calling Q, this point I'm calling P. Okay. So again, using Snell's law at AQC surface or interface, to whatever you want to call. When we apply Snell's law at this surface, the equation I get is mu sine R2 is equal to mu A, outside it's air, sine E. Mu I know is 1.5 times sine R2. Mu A is 1. Sine E is 90 degrees. Sine 90 degree is 1. Implies sine of R2 is 1 over 1.5. Now this means, okay, sine inverse of 1 over 1.5. Let's do this. What we'll get. So 1 divided by 1.5 is 0.66667. When I'll take sine inverse of this, wait, sine inverse of, okay, sine inverse of 0.6667, I'll get 41.81 degrees. 41.81 degrees. This is R2. Okay. Now, using Snell's law at A, P, B surface, what will it be? Mu A sine I is equal to mu sine R1. Mu A is 1, sine I we need to, okay, we have to find out angle of deviation actually. Okay, we'll see that angle of deviation. You have to find out angle of deviation here. Okay, we'll be able to find out. First, let's find out angle of incidence and incidence angle. Mu is 1.5 and R1. How to find out R1? Again, we know R1 plus R2 is equal to angle of prism. That means R1 is A minus R2, that is 60 degree minus 41.81 degrees. What will it be? 60 minus 41.81. That will give 18.19 degrees. This is R1. Now I'll substitute here sine of 18.19 degrees. Sine of 18.19, which is, okay, 0.312, and then multiplied by 1.5. That will be 0.468. Okay, I is this. So this is the angle of incidence, 0.468 degrees. No, wait, sorry. This is sine of I is this much. Now I will be, I have to take sine inverse of this. Sine inverse of 0.468 is 27.9 degrees. This is angle of, so yeah. Let's not focus on sine I. Angle of incidence is 27.9 degree. But what we have to find out is angle of deviation. Now again, if you remember, let me show you, we had found the relation which was telling us something. Angle of deviation is angle of incidence plus angle of emergence minus angle of prism. using this relation. So what just now we saw, angle of deviation is equal to angle of incidence plus angle of emergence minus angle of prism. Using this, angle of incidence is 27.9 degrees, angle of emergence is 90 degrees, angle of prism is 60 degrees. Doing this, 27.9 plus 90 minus 60 is 57.9 degrees, which here we don't have answers in decimals, so I'll round it off and then we'll get 58 degrees as the correct answer, angle of deviation. So you have to keep these relations in mind to find out the answers, otherwise it's pretty simple. Start with drawing the diagram to have all the things in front of you in form of picture, and then start applying these few basic laws. Now next question, just question number 8. The question is, a ray is refracted through a prism in such a way, we have this prism, in such a way that angle of emergence is twice the angle of, this is normal, say this is angle of incidence, let's say this is angle of emergence, this is R1, this is R2, this is angle A, and let's mark B, C, this is B, this is C. Actually I should not write A, P, B, I can just write A, B, side A, B and side A, C, but anyways, because we represent A, P, B triangle usually. Anyways, so angle of emergence is twice the angle of incidence, this is given. If the angle of deviation of ray is 30 degree, angle of deviation is 30 degree, we have to calculate refractive index of the prism. Consider the refractive angle of prism is 60 degree. A is 60 degree. Now what we'll start with is, let's first apply just found formula. Angle of incidence we know, angle of emergence we know, angle of prism we know. Okay. I mean, what we know is that it's double times angle of incidence. So let's apply this formula first to get some more things known. Ultimately, we have to find out refractive index of the prism. Okay. So applying this, that what was it? Angle of incidence plus angle of emergence minus angle of prism is equal to angle of deviation. Using this, angle of incidence is I, angle of emergence is 2I, angle of prism is 60 degree, angle of deviation is 30 degree. From this, 3I is equal to 90 degree. Okay, that means angle of incidence is 90 divided by 3, that is 30 degree. So from this relation, at least we could find out something, which is angle of incidence, that is 30 degree. Now we'll apply our Snell's law again. So from Snell's law, let's apply it for AB surface. Now I'm writing at AB, you can write APP or whatever. I mean it should be clear what we are doing, which surface we are talking about. It's good too because the straight line is AB, so it's good, I think, to write it as AB. So Snell's law, first we'll apply at AB surface, and the equation I'll get will be mu A sine I is equal to mu sine R1. Mu A is 1, sine I is 30 degree. Now sine 30 degree is half. Refractive index we need to find out. R1 we don't know, right? So I'll just leave it like this equation. Now I'll apply Snell's law on the second surface, which is AC surface. Okay. On this surface, the equation will be mu sine R2 is equal to mu A sine E Now mu I need to find out, sine R2 I need to find out, but mu A is 1 and emergence angle is 2 times I. That means emergence angle is 60 degree. Okay, so this will be sine 60 degree is, let me check, sine 60 is, instead of before going to sine 60 degree, actually we write it as root 3 by 2. That will be better way to write, because some trick we have to apply here. Okay, now let's multiply these two relations, equation 1 and equation 2, because here R1 is unknown, R2 is unknown, mu we need to find out. Okay, so let's use this relation. Let multiply 1 and 2. What will happen is half mu sine R2 is equal to mu sine R1 multiplied by root 3 by 2. This is what we will get. This half will be gone. And then further, or okay, let me not cancel out mu at least, because I want to find out mu. What we'll do is we can, okay, let me not cancel this half also. I want to use another trick so that I have to do less of maths, and the trick is something like this. I'll keep mu, let me rewrite this, mu sine R2 and mu sine R1 is equal to root 3 by 2 divided by, I'm taking this half on right side. Now we know something. What do we know? When do we get root 3 by 2? When sine is 60 degree. That means I can write it as sine 60 degree, and this sine, this is sine 30 degree. Okay, now one slide. Okay, now from this we can see that it's like taking this, here mu will be cancelled, and sine R2 by sine R1, this taking further, oh where is it, yeah, so mu by mu will be cancelled and I'll be left with sine R2 divided by sine R1 is equal to sine 60 by sine 30. Sine 60 degree by sine 30 degrees. That means, what does that mean? R2 that sine R2 by sine R1 is root 3, or even this thing we didn't need to do. Okay, sorry. We can just simply get it as root 3. Then this we know R1 plus R2 is A, so putting that, sine A minus R1 divided by sine R1 is equal to root 3. Or maybe we didn't need to do, we can just simply, I thought we can use some trick, but then it's not required. The sine R2 anyway, it will get cancelled, this will get cancelled, we'll be left with root 3. But directly also you can see, that way, this way, anyway is fine. Now further, let's go further. For sine relation, sine x minus y. When we expand, we get sine x cos y minus cos x and sine y Using this identity, we'll expand this and we'll get sine of A cos of R1 minus cos of A sine of R1 divided by sine of R1, which is equal to root 3. Okay. Now sine of A is 60 degree. Using that, sine of 60 degree, okay, and cos R1 did I find out? No, we did not find out R1. I did not find out R1, right? Okay, so let it be R1 cos of 60 degree and sine of R1, okay, divided by sine of R1 is equal to root 3. Now let me divide this numerator by sine R1, then I will get sine of 60 degree, and cos divided by sine will be cot. Cos divided by sine will be, wait, not this, cos 60 degree will be cos 60 degree, and sine R1 divided by sine R1 will be 1. This will be root 3. Now sine 60 degree is root 3 by 2 multiplied by cot R1, and cos 60 degree is half. Okay, from this, root 3 by 2 cot R1 is equal to root 3 plus half. Okay, that means I need a little bit more space. So this will be, okay, where is my cursor? So the cot R1 will be, if I multiply, it will be 2 root 3 plus 1 by 2 divided by root 3 by 2. That means cot R1 is equal to 2 root 3 plus 1 by 2 multiplied by 2 by root 3. Okay, so this is how it looks. Now if I'll take reciprocal, then reciprocal of cot will be tan, and it will become root 3 divided by 2 root 3 plus 1. Now tan inverse of this will be, let me calculate. Okay, now root, where is it? Square root of 3 square root of 3 is 1.732. That multiplied by 2 is this plus 1. That means 4.464. Then I will take tan of this. 1.732 divided by 4.464 is equal to 0.3879. All this is what equal to tan R1. That means R1 will be tan inverse of this 0.38799. So the value will be tan inverse of 0.38799, which I am getting to be 21.2058. or if you want to write only 2 up to 2 decimal digit, you can write 21.21 degrees. This is R1. So we can find out R2 also, which we don't need, but A minus R2 it will be, A was 60. What just happened? Got vanished. Okay, I don't know what just happened. I don't know how this happened. Just now I had calculated all the values and I had got R1 is equal to 21.2 degrees something. I don't know why it vanished. It was strange. Anyways, so this is what I got. Now what we need to finally find out is refractive index of prism. Okay, so refractive index of prism now will be sine of, or we can do delta m delta, we cannot use because this is not minimum angle deviation, this is simply angle of deviation. So we will use Snell's law instead. Using Snell's law, what we will get, mu a sine I is equal to mu sine R1, right? And we need to finally find out mu. Now mu a is 1 and incidence angle was 30 degree, sine 30 degree. Mu we need to find out, and sine of 21.2 degrees. Sine 30 degree is half. Now sine of 21.2 is 0.3616. It implies that, and this is 0.5. Mu is 0.5 divided by 0.3616, that is 0.5 divided by 0.3616 is 1.3827 is the refractive index of our material, and the answer, if we approx, is 1.38. So A is the correct answer. I don't know why the calculations vanished here, but yeah, okay, this is the correct answer. Now, 9th question is, a glass prism having the refractive index of its material, okay, this is my glass prism, refractive index is √3. What is the angle of minimum deviation when angle of minimum deviation is equal to refractive angle of prism? A, B, C, and this is given, okay, that angle of minimum deviation is equal to angle of prism, then find out refractive angle of prism. Okay, this information is given, relation is given, but we have to find out A. A is what we need to find out. Okay, then let's use our this formula, that refractive index of this medium will be sine of delta m plus A by 2 divided by sine A by 2. Now we know these are equal, so I can use sine, it will be A, because A plus A will be 2A divided by 2, it will be A, sine A by sine A by 2 is equal to this. Now if you know something, sine 2 theta is written as 2 sine theta cos theta. Okay, sine 2 theta is written as 2 sine theta cos theta. Here 2 theta, if you consider 2 theta is A, then this will become, mu will become 2 sine A by 2 cos A by 2 divided by sine A by 2. Sine A by 2, sine A by 2 cancelled. We will be left with mu is equal to 2 cos A by 2. Now mu is √3, root 3 and divided by 2 is equal to cos of a by 2. Okay, now root 3 by 2 is actually cos 30 degree. Okay, that means 30 degree is a by 2. That means a is 30 degree multiplied by 2, that is 60 degree. So the correct answer is D. 60 degree is the angle of prism. Now the last question for this interactive session is again for a prism. Actually, I think in maybe this time your assignment, this week's assignment has question on focal length and these also, but we already did many questions based on that earlier using Lensmaker's formula, so I think you can take care of those aspects. So that's why I'm only focusing on prism, which is the new thing that we have learned this week. So that's why I'm doing all the questions on this new part, which is prism. The refractive angle of prism is 60 degree. This should not go out. I'm not able to control this pen properly. It's 60 degree, and refractive index of material of prism mu is root 7 by 3. Okay. What is the limiting angle of incidence of a ray that will be just transmitted through the prism? Means limiting angle of incidence of ray that will be just transmitted. It is the same case that what should be the angle of incidence so that light is just coming out, means it's 90 degree, light just comes out of the prism. Again the same situation, that means emergence angle is 90 degree. So let's apply Snell's law on AC surface. Let's apply Snell's law for AC surface. Then it will be mu sine R2 is equal to mu A. Again this will be R1, and this will be R2. Okay. Mu A sine E. Mu is 7 by 3. R2 we don't know yet. Mu A is 1, sine E 90 degree, that means 1. It implies that R2 is sine inverse of 1 divided by this, means root 3 divided by root 7. Now sine inverse of this, when I will find out, I will get it to be, okay, wait, what happened? So root of 3 so this will give us 40.89 degrees. So R2 is this. Now again using R1 plus R2 is equal to A, we'll find out R1, which will be 60 degree minus 40.89 degrees. What will be this? 60 minus 40.89, that is 19.11 degrees. Okay, so this is R1. Now applying Snell's law, where is my pen again? Yeah, applying Snell's law on AB surface, we'll get mu A sine I is equal to mu sine R1. Mu A is 1, sine I need to find out. Refractive index is root 7 by 3. R1 is sine of 19.11. When I'll calculate this, sine of 19.11 is 0.327 multiplied by root 7 and divided by root 3 will give us the value, which is 0.5, means it is half. Okay, and sine I is half when I is 30 degrees. That means correct answer is 30 degree. Okay, So these were the 10 questions that we have. As I said, from previous years, same course, same week, but they're all majorly focused on PRISM because that is the new thing we learned. And if you have doubt, you can ask. And next week we'll be doing some other, I think, more experiments we'll be discussing on based on PRISM, and then corresponding working principle and the numericals based on it. So this was this week's thing. If you have questions, I can take. Just a minute. I'll stop there.